Hello, welcome to this video. We'll go in this video over a review of complex numbers. As I explained in class, we need complex numbers for all AC analysis, knowing how to deal with phasors. Phasors are complex numbers, so we must really master all the basic operations of complex numbers. So I will go over these complex numbers and I will show a number of examples that help illustrate the different operations. A complex number is a quantity that has both a real part and an imaginary part. The imaginary part is multiplied by this quantity. We use for this quantity the symbol I or the symbol J. This is a square root of -1. So we call this one the real part of the complex number. We call B the imaginary part of the complex number. Okay? The interpretation of the complex number is different in different fields of science. In our area, a complex number will represent a voltage or a current, a sinusoidal voltage or a sinusoidal current to be more specific. Okay, it can also represent an impedance. An impedance is the equivalent of a resistance in AC. We'll get to that very soon. Okay. Pictorially, if you want to draw a graph of this, this is called the complex plane. This is the real axis. This is the imaginary axis, and every complex number is a point in this plane. Okay, so this is a complex number z1, which is 3 plus 4i. So you can see I have 3 units in the real direction, and I have 4 units in the imaginary direction, so this gives me the point z1. The point z2 is -3 plus 4i, so the real part is negative, so we have to go in this direction, not in this direction. We have to go in this direction 3 units, and then the imaginary part is positive, it's 4. So this point here is -3 plus i4. Okay, z3 is this one here where both of them are negative. So if you go down this way, so the real part is negative and the imaginary part is negative. This is 3 units here and 4 units here. It's not drawn perfectly to scale, but I'm just trying to illustrate the idea. So this is a point z4, 3 minus i4. So the real part is positive and the imaginary part is negative. Okay, so this is positive real part, this is negative real part. This is positive imaginary part, this negative imaginary part, and every complex number represents a point. Later we're going to be using phasors, and a phasor will be represented not by the point but by the arrow that's extending from the origin to that complex point or to that point. So this is the corresponding phasor here for the point z1, this corresponding phasor for the point z2, corresponding phasor for z3, and so on. Okay, so this is called the complex space. This is called the first quadrant in the complex space. In this first quadrant, both the real and the imaginary parts are positive. This is called second quadrant. In this second quadrant, the real part is negative, but the imaginary part is positive. This is called third quadrant. The real part is negative and the imaginary part is negative. This is called the fourth quadrant. The real part is positive and the imaginary part is negative. Okay, so one other way of looking at a complex number is its distance from the origin and the angle it makes with the real axis, with the positive direction of the real axis. For example, this is a complex number z1. This is its angle theta, and this length here we call it r1. Its modulus, its length. Okay, so every complex number can also be defined by this number, which is r1, this length here, which is called the modulus of r1, and the angle theta 1. The angle theta 1, the first quadrant, is between 0 and 90. In the second quadrant, it would going to be 90 to 180. In the third quadrant, 180 to 170. In the fourth quadrant, 270 to 360. We can also have negative angles, so you can measure the angle in the opposite direction. So maybe the angle of Z4, you can consider it to be this very large angle, okay, which is, if this is 45 degrees, so this is going to be 2 pi minus 45 degrees. or you can simply write it as minus 45 degrees. So I just want to clarify this for you because it's very important. For this Z4, I can talk about this angle here. Okay, this angle, there are two ways of writing it. The first one is to measure it from the real axis, so you have to go all the way to here. So this, if this is 45 degrees, this will be 2 pi minus 45 degrees. Or you can simply say that the angle is minus 45 degrees because you are measuring it not in the counterclockwise direction but the clockwise direction from the real axis. So if this is 45, I can say that the angle of Z4 is minus 45 or 2 pi minus 45. Both of them are the same. Remember, sine and cosine functions, they are periodic functions and they repeat themselves every 2 pi. So adding an angle of 2 pi would not make any difference. So this figure illustrates what I said about what we call the polar form. The previous expression z equal to a plus ib is called the Cartesian form or the rectangular form. This form here is called the polar form. So you represent this is a complex number. It's a point in the complex space. You can identify it by r, the length from the origin. We call this the length or the modulus, and the angle theta it makes with the positive real axis. So mathematically speaking, you can write z as r e to the I theta. I use I and j. Both of them I mean the same thing, square root of minus 1. But sometimes when I put it in the e to the j, e to the I theta, I find j works better. There is something called Euler's identity. It says that e to the j theta or e to the I theta is equal to cosine theta plus I sine theta. So you can simply multiply r by this one, you get r cosine theta, and you multiply r by this one, you get I r sine theta. So this is what we used to call a. This is the real part of the complex number. This is the imaginary part of the complex number. So a is r cosine theta and b is r sine theta. So what's happening here, there are two ways of representing a complex number. I can write it in the rectangular or Cartesian form a plus ib, or I can write it as r e to the I theta. This means r e to the I theta means that the modulus is r and the angle is theta. Using Euler's identity, I can expand this one, and then when I compare them, I see that a is r cosine theta and b is r sine theta. So if I know r and theta, I can get a and b. And if you take the square of a and take the square of b, this will give you r squared cosine squared theta. This will give you r squared sine squared theta. If you sum them, you get r squared. So we know that the modulus is the square root of the real part squared plus the imaginary part squared for any complex number. And if you want to get the angle theta, simply divide this one by this one. You see that the r will cancel with r. Sine theta of cosine theta will give you tangent tan of theta. So theta will be the inverse tangent of b over a. So if I know r and theta, I can get a and b from this one. If I know a and b, I can get r and theta from these relationships. So remember, the modulus of a complex number is the square root of the real part squared plus the imaginary part squared. The angle of a complex number is the inverse tangent of the imaginary part over the real part. If you know r and theta, then you can get the real part and the imaginary part through these two identities here. These things are all very, very important, and we use them over and over again without thinking too much about them. Let's have an example. We are given here two complex numbers, minus 2 plus 2i, and z2 is equal to 3i. We would like to find the corresponding polar representation, and would like to draw these two complex numbers in the complex plane. So this is a for the first complex number, minus 2. This is b for the first complex number, is 2. Here a is 0 and b is equal to 3. So we're going to use the identity that the modulus is the square root of the real part squared plus the imaginary part squared, and that the angle is the inverse tangent of the imaginary over the real. Okay? So let's consider the first complex number. Z1 is equal to minus 2 plus 2i, so this is equal to a plus ib, the real part, plus I, the imaginary part. So a is minus 2 and b is 2. So you can get the modulus of the complex number z1, which I called it here r1, is square root of the real part squared plus the imaginary part squared. This will give you minus 2 squared will give you 4. This will give you 2 squared will give you 4. So this will give you 2 square root of 2. Now let's get the angle. The angle theta of this first complex number is by definition the inverse tangent of the imaginary part divided by the real part. Okay, so it's going to be the inverse tangent of, I wrote here as minus 2 over 2, but this is not really correct. I should maybe correct this one. It is the imaginary over the real. So the imaginary is positive, okay, while the real is negative. This is very important here when you try to you deal with complex numbers. Of course, now I would like to make a small warning. If your calculator accepts the real and the imaginary part, then you are going to give it an imaginary part of 2, real part of minus 2 is going to give you the correct answer. But if it accepts only one number, so inverse tangent of minus 1, if you give to a calculator inverse tangent of minus 1, what's going to be doing, it will simply give, if this is the complex domain, complex space, it's going to give you minus 45 degrees. So it's going to say the angle here is minus 45 degrees, minus pi over 4. But for minus pi over 4, this is the real part, this is the imaginary part. Okay, you can see for minus pi over 4 that the real part is positive while the imaginary part is negative, but this is not what you have here. Okay, so what you have to do, you have to add to this minus pi over 4 another pi in order to get the correct answer. So what you have to do really, you have to reflect it along this axis, and you add another pi, and this angle here would be this angle here, which is measured from this part, is gonna be 3 pi over 4. Okay, so let me repeat this one again. If you give your calculator minus 1 and ask it to calculate the inverse tangent of minus 1, it will give you minus pi over 4. So it will tell you you are in the fourth quadrant. Remember, minus pi over 4 means you are in the fourth quadrant. But in the fourth quadrant, the real part is positive, the imaginary part is negative. But this is not what you have here. Here, the real part is negative, the imaginary part is positive. In order to reverse the sign of the real and the imaginary, because you know, as the sine and the cosine, if you add pi to their phase, you reverse their sign. So what you have to do, you have to add to this angle a pi. Okay, so it's minus pi over 4. If you add to it a pi, you get this angle here. So the angle is measured from the real axis. So this angle will be 3 pi over 4. So this is a very common mistake many people would do. Be extremely careful, and if your calculator accepts both the real and the imaginary as inputs, it's fine. But if it accepts only the ratio, you have to be careful what quadrant you are getting in your answer. So I now know that Z1 is 2 squared 2 e to the j 3 pi over 4 r e to the j theta. This is the polar form. Now let's talk about the second complex number. Z2 is equal to 3i is equal to ib. There is no a here. There is no real part. So b is equal to 3. The modulus of this, because you're going to take the square root of the real squared, which is 0, plus the imaginary squared, which is b squared, will give you b. B here is equal to 3. Now, this is a purely complex, a purely imaginary quantity. So theta, by definition, is the inverse tangent of the imaginary part of the real part. This will give you the inverse tangent of infinity. Inverse tangent of infinity will give us pi over 2, which is correct. Because if you try to see this complex number here, if I draw the plane, it is here somewhere. It is 3i. Okay? But 3i makes an angle of pi over 2 with the real axis. So this is real and this is imaginary. Okay? So it's indeed the answer is pi over 2. But remember, if this was minus 3i, if this was minus 3i, if you give it to the calculator, it will give you, depending on if you give it, you can't give it really minus infinity, you still give it infinity. So just remember, in that case, it's gonna be here. Your complex number will be minus 3i. So the angle in this case is minus pi over 2, or is equal to 2 pi minus pi over 2. Okay, so it is 3 pi over 2. Just be careful with these signs. You can make big difference in your answer. And here I plotted these two complex numbers. This is Z1, it has negative real part, has positive imaginary part. This is Z2, it has only imaginary part 3. You can see the real part here is 0. Its projection, the real axis is 0. Now we need to do operations with real and imaginary with complex numbers. As you will see, we'll be adding currents together to apply KCL in the AC case. We'll be adding voltages together to apply KVL. So addition and subtraction of complex numbers is done on the rectangular, which we call it also Cartesian form. So if Z1 is A1 plus IB1, if Z2 is A2 plus IB2, then when you sum them, you sum the real plus the real and the imaginary plus the imaginary. So this is what I did here. Real plus real give you A1 plus A2. Imaginary plus imaginary give you B1 plus B2. So this is now the real part of the nuke of the sum. This is the imaginary part of the sum. If you subtract them, again you subtract real minus real and the imaginary minus imaginary. Okay? And then you take it from there. It's very simple. It has to be done in rectangular form. We cannot do it in polar form. Polar form is more suitable for division and multiplication, and as I will show you later in examples. Pictorially, illustration here, it's really like adding vectors. If this is a complex number Z1, this is a complex number Z2, and you want to calculate Z1 plus Z2, you draw Z2 from the end of Z1, and then this will be the complex number of the summation. It's going to be here somewhere. Okay, of course if you want to subtract, then you have to reverse this vector first, and then you add it to Z1, so it's going to be here somewhere. So I can, if I want to do subtraction, Z1 minus Z2 is equal to adding Z1 to minus Z2. So what you have to do first, you have to draw minus Z2 from here. So this will be minus Z2, it will go this way. Okay, you can see it's going on the opposite to Z2, and this will be here the summation of Z1 plus minus Z2. Okay, we're going to show how this can be used later with phasors. We'll be summing currents together graphically to apply KCL. We'll be summing voltages together graphically to apply KVL. Okay, so I will be talking more about this in other lectures. Let's have an example of summation. This is Z1, 3 plus 4i. This is Z2 minus 1 plus 5i. This is Z3, 3 minus 4i. We would like to find Z1 plus Z3, Z1 minus Z2, and Z2 plus Z3. Okay, if you add Z, you first get Z1 plus Z3. This is Z1, Z3. You see that they are identical except that the imaginary part here is 4 and the imaginary part here is minus 4. So when you sum them, you get the real part multiplying with 2. So this will cancel with this one, and as we agreed, we sum the real plus the real and the imaginary plus the imaginary. These two will give you 0, while these two will give you 6. So you end up with 6. This number here, which is Z3, we say this is the conjugate of Z1 because it has the same real part, but it has an imaginary part with opposite the sign. So it's called the conjugate of Z1. And this has very useful applications, as we'll see later. Let's subtract Z1 minus Z2. So Z1 minus Z2 means you subtract real minus real plus imaginary minus imaginary. So this will give you 3 minus 1. It will give you 4. 4 minus 5 will give you minus 1. So this is what I did here. Real minus real, imaginary minus imaginary. 3 plus 1. And I wrote here this is minus 1. So I changed the sign of these two already, okay? So 3 plus 1 will give you 4. 4i minus 5i will give you minus I. The last thing is to sum Z2 and Z3. So you get minus 1 plus 3 will give you 2. And you get 5 minus 4 will give you 1. So you get 2 plus I. This is the summation of Z2 and Z3. We mentioned the previous slide about complex conjugate. We introduce it here formally. If you have a complex number, which is Z equal to A plus IB, then its conjugate written as Z bar is A minus IB. It has the same real part, but has negative the imaginary part. When you sum them together, A will sum to A, you get 2A. B will cancel with minus B, so you get a purely real number, which is double the real part of the complex number z. The interesting part happens when you multiply them. If you multiply z and z bar, z is a plus ib, and z bar is a minus ib. This is a bracket with two terms. This is a bracket with two terms. So when you multiply them, you get a squared, you get iba, you get minus iba. When you multiply ib and minus ib, remember that I squared is minus 1. So this gives you here plus b squared. So this is purely real, this is purely real, and these two are imaginary. But these two are the same quantity with a negative number, so these two will cancel. Okay, so this will disappear with this one, and you end up only with a squared plus b squared. So when you multiply a complex number by its conjugate, you get the real part squared and you get the imaginary part squared. But this is a modulus squared. So this is something we know very well. When you multiply a complex number by its conjugate, you get its modulus squared. Okay, so here, for example, z is equal to 3 minus 4i. Its conjugate will be 3 plus 4i. If you multiply them, 3 with 3 will give you 9, minus 4i and 4i will give you 16. Okay, this will give you minus 12i. It will cancel with plus 12i. Then you end up with 9 plus 16, which is 25. But this 25 is nothing but the modulus squared, because the modulus of this complex number is the square root of 9 plus 16. Real part square plus imaginary part square. So r here is equal to 5. So remember this fact: when you multiply a complex number by its conjugate, you get the modulus of that complex number squared. Now we move to talk about multiplication, division, and we use them very often in our work. We apply Ohm's law in with AC signals. You divide a complex number representing the voltage by another complex number representing the impedance to get the current. I will be talking more about this in future lectures. But remember, this is used very often, multiplication and division. When you multiply the current, the phasor of the current, with the phasor of the impedance, you get the phasor of the voltage. And these are all complex numbers. Multiplication can be done in either rectangular form or polar form. I will show it for both. It's easier to do it in the polar form. So if z1 is a1 plus ib1, this is a complex number, this is its real part, this is its imaginary part. z2 is a2 plus ib2, this is the real part, this is the imaginary part. Let's multiply them. Real with real, a1, a2 will be real. When you multiply ib1 by ib2, you get minus b1, b2. This is also real because I squared is minus 1. Here, this will give you a2 multiplying ib1 and will give you a1 multiplying ib2. Now, let's put everything together. You get a1, a2 minus b1, b2. So, you got 4 terms. 2 of them are real and 2 of them are imaginary. So, you sum the 2 real parts. So, a1, a2 minus b1, b2. And you sum the 2 imaginary parts. a1 b2 plus b1 e2. Now you could have done the same exactly using polar form. z1 is r1 e to the j phi 1, z2 is r2 e to the j phi 2. When you multiply them, like any multiplication, r1 will multiply r1, so you get r1 r2, and the e to the j phi 1, e to the j phi 2, when you multiply e to the theta 1 by e to the theta 2, you sum the exponents. So this will give you e to the j phi 1 plus phi 2. Okay, so now we know when you multiply two complex numbers, the modulus of the product, this is the modulus of the product, is equal to the product of the two moduli of the two complex numbers. And the phase of the product is the sum of the two phases of the two complex numbers. These things we do them without much thinking, because we just use this in analyzing circuits. So we must be very fluent in this. You have to be extremely fluent in it. So remember, when you multiply two complex numbers, you get another complex number. The modulus of this complex number is the product of the two moduli, and the phase of the complex number is the sum of the two phases, as evident from this equality here. So we have here two complex numbers. z1 is 6 minus g8 and z2 is 4 plus g3. We'd like to find z1, z2, and we'll find them using the rectangular form. We'll find them using the polar form. Okay, using the rectangular form, you multiply 6 minus g8 by 4 plus g3. this bracket has two terms, this bracket has two terms, so you're gonna get four terms. 6 by 4 will give us 24. J3 by minus G8, remember J by G will give you minus 1, and again as I explained, I use J and I. Sometimes I taught with both, so I sometimes I switch without even thinking, but both of them mean square root of minus 1. J multiplied by minus G will give you minus 1. 8 by 3 will give you 24. So minus 1, and you have already minus 1, so this becomes 24. Minus G8 you multiply by 4, so you get minus J32. 6 you multiply by J3, you get J18. So if you sum the two real parts, if you sum the two imaginary parts, this is the answer you're going to be getting is 48 minus J14. Now, how can we do it in the complex form, in the polar form? You have to write every complex number first using in its polar form. So Z1 will be written as R1 e to the J phi 1. This is Z1. What is the modulus of this term? It's square root of 6 squared plus 8 squared. So this will give us 36. 36 plus 64 will give us 10. The square root of that will give us 10. The angle is the interesting part. The angle is the inverse tangent of minus 8 over 6. So it's minus 1.333. If you give it to a calculator, it's going to give you minus 53 degrees. Okay, which is correct. Why? Because this number is in the fourth quadrant. The real part is positive, the imaginary part is negative. And indeed in the fourth quadrant, if you measure the angle in the clockwise direction, the angle will be negative. So this answer is correct. I don't have to interfere and fix it. Okay, sometimes I have to add by to it, but this is not the case here, because indeed the imaginary part is negative and the real part is positive. If this was minus 6 and 8, and you gave your calculator the inverse tangent of minus 1.33, it's going to give you minus 53. But minus 53 is not the right answer, because if this was minus 6 and 8, minus 6 plus J8, then the real part is the one that's negative. You have to add by. So you add by to this quantity, and this will give you the answer. But here, this is correct. I can take this one as it is, and the reason for this, as I explained, is that if you take a look at this answer, the calculator is telling you you are in this quadrant. This one here is minus 53 degrees. Okay, minus 53 degrees. But indeed, in this fourth quadrant, the real part is positive, and the imaginary part is the one that's negative. So this is correct. To carry out the multiplication, we have to find also the modulus or the polar form of the second complex number. So here, this is the second complex number. I need to write it as R2 e to the J theta 2. You get the modulus by squaring, taking the square root of the real part squared plus the imaginary part squared. You get the square root of 4 squared plus 3 squared is equal to 5. This is 16 plus 9, give you 25, equal to 5. The angle, luckily these both are positive, so when you give to your calculator the inverse tangent of 0.75, 3 over 4, imaginary part divided by real part, your calculator will give you 36.869, and this is in the first quadrant, so this is correct because both of them are positive, so I can keep this one. Now I already do the multiplication. This is the polar form of Z1, this is the polar form of Z2. If you multiply them, multiply the modulus by the modulus, this will give you 50, and then you add the two angles. So minus 53, you add to it 36, you get e to the minus j 16.26. You can use Euler's formula to convert this to cosine minus 16.26 minus j sine minus 60. Actually, already moved the sign out, a negative sign out. Okay, so I could have written it that way. I could have written it as plus here, and then you have the minus inside the sign, because the angle that's negative, both are the same. If you do that, if you find the cosine and sine multiplied by 50, you will get this answer. The answer that we got using the rectangular form is 48 minus j14. Here, because I did not use sufficient number of digits, I end up by j13.9999, but they are identical. If you use sufficient number of digits, it should get exactly the same answer. The last thing I would like to mention in this video is division. When you divide two complex numbers, it's very important because Ohm's law says that the current is the voltage divided by the resistance, and EC circuits you say that the phasor of the current is equal to the phasor of the voltage divided by the impedance. So we're gonna use division of complex numbers. Okay, when you divide two complex numbers, you can do it using rectangular form or polar form. Rectangular form, you'd say you write Z1 over Z2. This is Z1, A1 plus GB1. This is Z2, A2 plus GB2. The trick they do here is that they multiply by the conjugate of the denominator in the numerator and denominator. So they multiply by this. So I'm going to multiply both sides by A2 minus GB2. You can see this is the conjugate of this one. And as a result, the denominator becomes purely real. This becomes A2 squared plus B2 squared. The imaginary parts here will cancel each other out. We agreed if you multiply a complex number by its conjugate, you get its modulus squared. So this gives you A2 squared here, and will give you the A2 squared plus B2 squared. Now in the numerator, you have a bracket multiplying another bracket, so you're gonna get four terms. A1, A2 will be real, and this one will give me P1, B2. Remember, J by G will give you minus 1, so it will cancel the sign. This will be the real part. This will give me JB1, A2 minus JB2, A1. So I can take J as a common term out. This will give me B1, A2 minus B2, A1. So this is how we do division in rectangular form. Of course, doing it in polar form is a little bit easier, as I will show you in the next slide. Okay, in polar form, you only divide Z1 by Z2. You write Z1 as R1 e to the J phi 1. You write Z2 as R2 e to the J phi 2. You move this e to the J phi 2 to the numerator and becomes e to the minus J phi 2. And then you divide the two moduli that you have here, and you end up with this form. Okay? But this division is equal to Z1 over Z2 is equal to R e to the J phi. This is the result of the division. So you can see that the modulus of the division is equal to the modulus of the first complex number divided by the modulus of the second complex number, while the phase of the division, the angle of the division, is equal to the angle of the numerator minus the angle of the denominator. So this is something we use without thinking. If you divide two complex numbers and you want to get their modulus, then the modulus is the modulus of the numerator divided by the modulus of the denominator. If you want to find the phase of the division, or the angle of the division, you call it the angle or the phase. This angle here is equal to the angle of the numerator minus the angle of the denominator. This is the rule we are going to be using, and it works fine for examples. And as you can see, doing the division here is way easier if you have the polar form. Let's have an example. We have two complex numbers. Z1 is minus 3 minus J2, and Z2 is minus 5 plus J3, and we would like to divide Z1 by Z2. Well, we're going to do it first using rectangular form, and then we're going to repeat it using polar form. So, rectangular form, you divide Z1 by Z2, so minus 3 plus J2 over minus 5 plus J3. As we agreed, you have to multiply by the conjugate of the denominator, so you have to multiply by minus 5 minus J3. So this, if in the denominator, this gives you the modulus of this term squared, so this will give you minus 5 squared is 25, plus 3 squared is 9. While in the numerator, you're going to be having this bracket here, multiplying this term, which is minus 5 minus J3 as shown here. So this is going to give us four terms. Let's see how we simplify them. Minus 5 by minus 3 will give us 15. Minus J2 you multiply by minus J3 will give you minus 6. Remember, J by J will give minus 1. And the minus will cancel the minus. So you end up, unfortunately, with a minus sign. So this will give you 15 minus 6. You end up with the real part of 9. What about the imaginary part? Imaginary part will come from minus 3 multiplying minus J3. So this will give you J9. And minus 5 multiplying minus J2 will give you J10. So J9 plus J10 will give you J19. So 9 plus J19 divided by a purely real number. And as you know from your previous courses, if you divide a complex number by purely real, you divide the real part by this purely real number, and you divide the imaginary part by this purely real number. Okay? So this will be 9 over 34 plus J19 over 34, and this is what you end up having here. Now we're going to verify that we can get the same answer using the polar form. But of course, to be able to use the polar form, I have to convert this one first to its polar form. I have to convert this one first to its polar form, and then I'll divide these two polar forms. So this is z1 minus 3 minus g2. I would like to write it as r1 e to the g phi 2, phi 1. So r1 is the modulus of this complex number, and phi 1 is its angle. r1 by definition is the square root of the real part squared plus the imaginary part squared. So 3 squared plus 2 squared. I ignore the negative signs, you don't really make a difference. So we end up by square root of 9 plus 4 square root of 13, which is 3.605. The angle. Notice that this is in the third quadrant, okay? If you give your calculator the inverse tangent of minus 2 over minus 3, the two negative signs will cancel. Again, this depends whether your calculator accepts the real and the imaginary together as two separate numbers, or you give it only the ratio 2 over 3. If you give it 2 over 3, it's going to give you an answer in the first quadrant, which is wrong. Okay? So this is very important to understand. So I'm going to draw here. This is the real axis. This is the imaginary axis. Okay? The calculator, if you give it the inverse tangent over 2 or 3, will give you a point here in the first quadrant. But this in the first quadrant, both the real part and the imaginary part are here. As you can see here, this real part is positive. The imaginary part is also positive. But this is not what you have. You have actually both of them negative. So what you have to do, you have to reflect it in the opposite direction, because which means you add a pi to the face. So what I did here, I added pi to the answer that the calculator gave me. I used the calculator that accepts only the ratio, and when I did that, I end up with an angle in the third quadrant, and this becomes 213.69. This is extremely important. I cannot even stress enough the importance of properly checking the angles you're going to get, because otherwise your answer will be completely wrong. If your calculator accepts both of them as separate numbers, good, then it's fine. But if you are used to only entering the ratio, which is 2 over 3, you can end up with an angle in the wrong quadrant. Let's talk about the second complex number. D2 is minus 5 plus J3. I would like to write this one as R2 e to the G phi 2. R2 is the modulus, so it's square root of the real part squared plus the imaginary part squared. So you get 25 plus 9 square root of 34, which is 5.83. I would like to get the angle. The angle of this complex number is the inverse tangent of the imaginary part divided by the real part, 3 over minus 5. And again, if you give your calculator minus 0.6, it's going to give you the wrong answer. Why? Because what's going to happen, your calculator will see, oh, this is 0.6, then it's going to give you an angle which is negative. Okay, so this is real, this is imaginary. Okay, then tell you the angle is here, it's minus 31 degrees. What is the answer going to be getting exactly? Minus 31 degrees. But for this angle, as you can see, the real part is positive while the imaginary part is negative. But this is not what we have here. We have the real part negative and the imaginary part is positive. So you have to reverse their signs. How do you reverse their signs? You add pi to the face. So what you have to do, you have to extend this line the other side, and then you add pi to the face. Okay, and if you add 180 degrees to minus 31, you get 149 as shown here. Okay, so the angle between here and here will be 149, which is the correct angle. The last thing to be done to divide these two complex numbers, I have the first complex number here, I have the second complex number here. As we agreed, when you divide two complex numbers, divide the modulus by the modulus, and then you subtract the angle of the numerator from the angle of the numerator. So this is phi 1, this is phi 2, and phi of the result will be phi 1 minus phi 2. While you divide these two here, if you divide this one by this one, you get 0.6183. If you subtract this angle from this angle, you get 64.69. I will use Euler expression, Euler formula to expand this one to cosine plus j sine. Okay, and then I calculate them, and then I multiply it by the modulus. I get exactly the same answer I got earlier by using the rectangular form. So division can be done using rectangular form, it can be done using polar form. You should get exactly the same answer as long as you are very careful about the angles and you are checking the quadrant in which your complex number is.